So we stopped at so helium neon laser is the second laser, which is a gaseous laser. First laser what we have discussed is ruby laser, is a solid state laser. Second laser system is a helium neon laser, or which is a gaseous laser system.
Sir, we are unable to see your shade screen, sir.
Yeah, just a minute, I'll do it. I'll share it again. Is it visible now?
Yes, sir.
Yeah. Now we have seen the laser system, helium neon laser system, one of the gas laser. Okay, we have done this experiment also in the lab. You found that the wavelength of the laser system is around 6600. Now we will see, okay, what is the wavelength that actually will get from the helium neon laser. But remember that helium neon laser is a gaseous 4-level continuous laser system. It emits the laser light continuously. That is most important for us. But a ruby laser is a solid state laser, 3-level, and it's a pulsar laser, means output is pulsed. Why helium neon laser gives you continuous? Why this ruby laser gives pulsed? This is because of pumping system. In ruby laser, we are using a flash lamp. That means it gives you only flashes. One flash will take the atoms from lower energy level to higher energy level. Once all the atoms in the higher energy level falls down, then population inversion is not there in ruby laser. If the population inversion is not there, you don't get a lasing output. Once again, if you give a xenon flash on, then ruby in the ruby laser atoms will again go to higher energy state and they will fall down. And again we'll get a flash. Therefore, whenever you are giving flashes of xenon, we'll get a flash of a laser light out of it. But in case of neon laser, helium neon laser, we get a continuous wave because the electric discharge is always on. When the electric discharge gas is taken here, what is happening inside the tube, quartz tube? Okay, we call this as a quartz tube, quartz discharge tube. This is the quartz tube. So when you take a quartz tube in which the gas is filled and the quartz tube is hermetically sealed, this is sealed or with the help of Brewster's angle. These are called Brewster windows, what we call it as. This is Brewster window. Brewster window. You know Brewster law. If the light strikes at an angle equal to angle of polarization, then the light is a polarized light. So the output is a polarized output. This is also a Brewster angle, Brewster window. What are the advantages of these Brewster windows? The advantage of these Brewster windows are: one, if the photon is exactly traveling parallel to this, okay, they will enter back as a feedback and they go it. If the photon strikes the mirror at some angle other than normal direction, the photon strikes, yes, I suppose the photon is striking somewhere here with an angle. It will get reflected and it cannot go into the active medium. They are going, if it making some angle and striking it, okay, at some angle and striking it, it go out of it. These are called cavity losses. Because of these losses, some of the photons may not be going into the active medium and to produce more photons. And if this is the photon is not striking at an angle of polarization, Brewster angle, this will go away and therefore we have losses. Therefore, there are losses in the cavity also. We have to overcome these losses and see that the losses are less when compared to amplification. That is also one of the important aspects you have to keep in mind. Now, if I look at this once, that is what where we have seen it. This is a continuous output we are getting. The here it is containing helium, neon, gas in the ratio 10 is to 1. 10 is to 1. Now what is happening? We have to say it. When you apply electric discharge here, a huge voltage or current is produced in the tube. That means there is a high electric field. This electric field makes helium atoms, and in the helium atom they remove one electron and it will be converted into helium ions. And these ions are positive ions. Okay, this is charged ions. Charged ions. When a charged ion is there within the electric field, they get accelerated because charged particle gets acceleration, and they'll become and acquire more kinetic energy. So that's why what we are saying discharge. When you discharge, you're ionizing the helium ions. So some of the helium ions in the discharge tube gets ionized and we have helium ions. Once it is ionized, that means you are removing an electron from the outermost orbit with the help of applied voltage. That means this tube contains helium ions and also electrons, because the electrons are removed from the helium atoms to get helium ions. So we have helium ions and also electrons. Both helium ions are charged. Yeah. So what we say is that, okay, from this, the discharge tube contains helium ions as well as electrons. Both are charged particles. Therefore, those get accelerated. Helium ions get accelerated because of the applied electric field, and electrons also charged particles, they get accelerated. But helium ions are heavier than electrons. Electrons are very lighter. Therefore, the helium ions which acquire kinetic energy by the applied electric field collides. These ions, okay, collides or make collisions with neon atoms. And thereby they transfer the energy to neon atoms, and neon atoms will become neon ions, and they go to excited state. That's why we need helium atoms to make the neon atoms to go to excited state. Okay, we are making helium atoms to go to excited state by applied electric field. And taking energy, they get accelerated. Accelerated, okay, helium ions. Because if you take atoms, atoms cannot be accelerated because they are electrically neutral. Only ions or electrons or charged particles can be accelerated in a electric field. So whatever the electric voltage you're applying, that creates electric field within the tube. Therefore, we have helium ions, electron ions, helium ions also. But the number of helium atoms are much more larger, 10 times larger than neon atoms. Therefore, the probability of helium atoms colliding neon atoms is more when compared to the reverse, that is neon atoms colliding with helium atoms. Therefore, we have the neon atoms in the excited state. Then how do I get lasing action from this? If you want to say it, then okay, I will be looking the energy level diagram of helium neon laser. So I draw here the energy level diagram of helium neon laser, which is a very, very important one. So one of this is I am first drawing energy levels of helium. This is a helium atom I am taking. and helium atom ground state is this. And I am taking two excited levels of helium having energies. Okay, I call this maybe F1 is the energy level, first level for helium, F2, F3. These energy levels are slightly different values, 9.81 electron volts. This is 20.61 electron volts. Because of discharge, what we call electron impact, okay, because of ionization, helium atoms in the ground state, they will be taken to higher energy levels. Okay, once they have taken, here we have neon energy levels. Separately, I'm drawing it. Later, we'll see how the energy will be transferred. So if you look at this, we have so many energy levels of uh, neon. So if you look at these energy levels are very close to the energy levels of helium. Helium is having 20.61, whereas it is also having 20.66. It's a difference of 0.05 electron volts, which is a very small and can be obtained at thermal energy. Therefore, these are the energy levels of helium and also neon. Now, the energy should be shifted from the excited helium atoms to the neon atoms in the ground state, and I have to lift the neon atoms by the help of excited helium atoms to higher energy levels, because the helium atoms are already in the excited state by the electric discharge, which we call as electron impact, and these energy levels are almost equal to neon. Therefore, it is easy to take the neon atoms to higher level with the help of the helium atoms. Since helium atoms are having energy levels close to this, therefore the transfer of energy from the helium atoms to neon atoms is very easy. That's why the helium atoms are helping to get population inversion in neon atoms. And you look at the energy level states, what we have shown it. You draw the diagram how I am drawing here on the screen. Now we look at this one. Just a minute, I will share it again. Okay. This is the energy level diagram, whatever we have drawn it. Now here I will see the advantage of these values. The values which we have given for energy levels of helium and neon, they are very, very important. And I will now write here the different energy levels that what we are using for lasing action in helium neon laser. If I take helium neon laser, these are the energy levels that are there in it. But if I write more or less, you can see the energy level that are involved maybe around, I can say that the ground level of helium is roughly 1s level. This is 1s level. And this level, whatever you are getting 2.61, this is 2s level. Okay, you know 1s, 2s, 2p levels. This is 2s level. This is 1s level. Okay, so then if you go here for helium, this ground state what we are taking from this is 2p level. And then if you go to higher value, I call this maybe around 3s level. This is 3s level. And this is 18.7 is 3p level. I'm taking 3p level. And then this may be 4s level. 4s level. When you're writing electronic configuration, use this. Okay. And then we have this as 5s level. 5s. This is 5s level. So we have 5s, 4s level, and we have okay a 3p level also. Additionally, I have given one more level also here. Okay. Now these are the energy levels. If you take 3s level, this may be at 16.7 electron volts. And then how I'm getting CS. Now, this is energy transfer by collisions. That means the helium atoms, and they are accelerated in the tube, they are in continuous motion because their kinetic energy is increased because of applied electric field. As they move, they collide with the neon atoms. Because the neon atoms are less in number compared to helium atoms. Therefore, helium atoms has more chances to collide with neon. Hence, this is called as preferential transfer of energy. We call it as preferential transfer. Preferential transfer. Why preferential? The neon atoms preferably to collide neon atoms so that they will be excited. That is our preference. Not neon atoms to take helium atoms to up. So thereby we will take this. These are the energy levels. Once they have taken it, but I know that this is a metastable state. They can, okay, this is a metastable state. And as well as this neon, if I take it, this is also a metastable state. This is also a metastable state. Therefore, the time is more for them. Then I'll see the transitions. Once the energy is transferred from the helium atoms to neon atoms in the ground state, they will rise up. Therefore, I have population inversion there. Then we see it wherever we are getting here. If you see it, okay, there is a transition from 3s to this level, giving you 3.38 micrometers laser. This is the laser light. Okay, but the difference is small, and this is not in visible region. This is the one possibility of transition. Next possibility is some of the atoms from 5s level, they also fall down into 8. The energy difference is large if you see here when compared to the previous transition. Therefore, we'll get laser action 6328 angstroms. This is our required lasing action. But there is another possibility that atoms can fall to 4s level from 5p. That means they may fall here. From this is a metastable state again 4s, and this may be falling to this 3p level also. Therefore, there is a chance of probable transitions, okay, between 5s to this state or 5s to this state or 4s to this state. All of them are yellow transitions. 3 of them will give you laser beam. So, but if I adjust distance between the two mirrors, okay, that is the length L between this two is equal to n lambda by 2 and lambda is equal to 2L by n. If this L is adjusted for this lambda, then this lambda only will come out of the 1 and this will be suppressed. So the helium neon laser gives you 3 transitions, 3.39 micrometers, which is not in visible spectrum, and 1.15 micrometers, it is in IR spectrum, and the laser 6328 is in visible spectrum. Again, 63 is a red color. I'll get the emission is red color by helium neon laser also. Ruby laser also gives it red color, red laser. Okay. So thereby you have to adjust the distance between the two mirrors so that L equal to this lambda. This L satisfies this wavelength lambda. So thereby we will get a light coming out from the neon helium, okay, helium neon laser with a wavelength of 6328 Armstrong units or 632.8 nanometers red color. But still, if the atoms are falling from 5s level to lower level, this is still higher level when compared to ground state. So I do have more atoms here in the in the excited state than the ground state, because this level is also excited level. Okay, and if I call these levels instead of E1, E2, okay, E3, we have E4 and E5 is this, and maybe E6 is this, I call it as. So, but still E3 is having higher energy than the ground state. Therefore, the atoms in this one, this transition gives you the laser required for us. These are also lasers, but they can be suppressed by adjusting the distance between the two mirrors in the resonating cavity. Then we have red here, and these atoms will fall down by giving spontaneous emission. This is spontaneous emission of wavelength 600 nanometers. Therefore, this is not laser. This is spontaneous one. And this will not come out of it because the wavelength is different, since the resonating column distance is different. So not laser, but it is spontaneous. Here is a stimulated beam. Stimulated beam gives you a laser with a coherent emission. This is stimulated emission. The emission from E6 to E3 is coherent and gives you laser light in visible spectrum at 6328 angstroms. But this is spontaneous emission around 600 nanometers, which is also red in color. But it is spontaneous emission. And this is still is a higher energy state compared to the ground state. Therefore, this will fall down here, radiationless transition. How they fall radiation transition? Because they have started coming from E6 to E2, where while coming they have lost much energy because of the transitions from E6 to E5, some of them E6 to E3, some of them from E4 to E3. And then E3 to E2, they have lost most of the energy. So they have a little energy in E2. And while they are moving because of applied voltage within the tube, whatever you are taking, the quad tube, they collide with the walls of the tube. When they collide with the walls of the tube, they lose whatever the energy, and therefore they lost the energy and will come to the ground state. So this is a radiation transition. This is because of the loss of energy due to collision, okay, with the walls of the tube. Okay, and when they are simply colliding with the walls of the glass tube, okay, that is Brewster angle tube, they lose the energy and therefore they'll come here. Because when they're coming from E6 to E2, they have lost much of the energy. And whatever the little energy they are there, if they collide with the walls of the tube, because the tube should be made very, very narrow, they won't make it. Because of narrow, the collisions are more, okay, and thereby they lose the energy, they come here. This is the collisions with the walls of the tube, and thereby the energy will be lost, and hence they'll come to the ground state again. But the atoms which are coming to the ground state is again the discharge is on. Therefore, helium atoms will again always be there in the metastable state. Therefore, the helium atoms which are there already in metastable state because of continuous supply of voltage, they will again collide with the neon atoms which are coming to the ground state. Therefore, they go again up and they will fall. Some of them will fall and they will be taken up by the helium atoms. Therefore, okay, whatever the atoms that are coming down, there will be again collision with these helium atoms. They go again up and they come down again. While they're coming down, they will be pushed by these helium atoms again up. They'll come. That means always I have some atoms in the higher energy metastable states. That means always the population inversion is there. Population inversion is not depleted. Hence, always the laser beam will come out of the system. Thereby, we have continuous laser output here, which we call it as continuous wave Okay, laser output, that's we call it as. But that is not the case when I take the ruby laser. Ruby laser, that we have only one simple ruby flash, then light comes, again it stops. So therefore a ruby laser cannot give continuous output. It gives only pulse output. Whereas helium laser, we have continuous population inversion in the higher energy state because of the transfer of energy by helium atoms to the atoms in the ground state. Therefore, always I do have okay population inversion, thereby laser emission is continuous. This is what we call it as energy level diagram of a helium neon laser. And you have to draw these diagrams very clearly. Okay, so this is a preferential transfer. That means the chances of helium atoms more in number colliding with the neon atoms less in number is more. Thereby, we always get a population inversion and metastable states in the metastable states. Thereby, you have the lasing action in a continuous manner. Now, we will look at the next laser called carbon dioxide laser. CO2 laser is most important laser for the civil and mechanical students because it is used in industries, which is a powerful laser and having special applications in industry for cutting, welding, drilling. Whereas the helium neon laser and ruby laser are not so powerful and they cannot be used for industrial applications because their power is much less compared to CO2 laser. Now we will look at the next type of laser called carbon dioxide laser. So again, it is a gas laser, but it's a molecular laser. Okay, here we have taken helium is in a gas, monoatomic gas. It's not a molecular gas, but carbon dioxide CO2 is a molecular gas. Therefore, carbon dioxide is a molecular gas laser, and it gives you continuous output. But however, you can make this continuous output as a pulsed output also. Therefore, you can operate the CO2 laser, okay, either in continuous mode or pulsed mode, your choice. Any continuous laser can be converted into pulsed mode, but pulsed mode cannot be converted into continuous mode. Its output is continuous or continuous wave, continuous, or we say pulsed. That is, you have to make it or pulsed. So you can make into one. And CO2 laser lasing action is achieved due to transition between vibrational states. That means carbon dioxide molecular structure, you know. Roll number 59. Are you online? 59. Vijay. Roll number 59. 59. 58. 58. Vedasri. Veda. Roll number 51.
Yes, sir.
Srija, do you know what is the bond angle in hydrogen water?
104.35
Yeah,
something.
yeah. What is the bond angle in carbon dioxide?
180 degrees.
Yes, it is a linear molecule. That is very good. See, so that is very important. Okay. carbon dioxide laser when you're using, okay, carbon dioxide is a linear molecule. That's why the angle is 180 degrees. But when you take, okay, I'm sharing the screen here again. Okay, now if you take a water molecule, okay, water molecule is something like we write H2O and O will be somewhere here. We have H and H with a bond angle. This is the bond angle we call it as. But if I take carbon dioxide CO2, we have C here. This is the C. We have a bonding with oxygen O and we have another oxygen here, double bonding. And this is a linear molecule. This is the linear molecule having an angle of 180 degrees. This 180 degrees linear angle in the carbon dioxide makes some important vibrations by the carbon dioxide molecule. And that molecular, okay, vibrations we call it as vibrational states we call, or vibrational energy states we call it as. And those vibrational energy states are different and we use those vibrational states. I will show those states also in the figure, and those we will use to get lasing action. So most important thing you should remember here is, okay, what type of the energy levels are involved in the, okay, CO2 laser is important for us. So we have a carbon dioxide laser is a gas laser. It is a 4-level laser and it may be a continuous or pulsar laser. But important thing is that lasing action is because of the energy changes or transitions between vibrational states of carbon atom or carbon dioxide molecule. This is important. But what are the three components in the CO2 laser? In CO2 laser, we have again active medium, pumping, and a resonating column. Three are there as three components of laser. The active medium in CO2 is not CO2 alone. It's a mixture of carbon dioxide and also N2 along with, okay, if you say it along with the helium, we have N2 gas. So we need the active medium. Active medium and lasing action is provided by CO2. But helium, N2 nitrogen and helium, if you take these two, okay, we use them, helium and neon, to get nitrogen to get excitation as we get in helium neon laser. That means the function of helium is same as that of helium neon laser in carbon dioxide laser also. So the transition takes place between vibrational states of CO2 molecule. That is most important, and we have to see what are the vibrational states of a linear carbon dioxide molecule. But how do I get pump? I'll get the pumping is electrical discharge similar to helium neon laser. So most of the gas lasers like helium, most gas lasers use pumping as electric discharge. Pumping as, okay, electric discharge. So pumping mechanism in most of the gas lasers is electric discharge only, because the gases can be discharged very easily by applying electric field. That is one of the important thing you have to remember in this. Now we will also look at the resonating column. Because CO2, N2 and He are gases, they are simply gases, we use those gases which are taken in a closed quartz tube or a glass tube. Therefore, we have to take a tube and fill the tube. Okay, I'll take a tube, something like this. I fill this tube with CO2 plus N2 plus He at some pressures or their partial pressures. I have to keep it. That is very important. Okay. And then this is filled with this, and I put here two mirrors. That means active medium should be placed between the two mirrors. But to effectively get more number of photons that are focused into the active medium, instead of taking plain mirrors, I take confocal or concave mirrors, something like this. So these are the mirrors I take it. The advantage of taking mirrors is that even though one photon going in a direction not parallel to this, okay, if you're going in some this direction, while hitting it will come back. Therefore efficiency can be increased. If I take a parallel one, if it is some angle, it goes out. Therefore it is out of the system, hence number of photons will decrease, intensity decreases. To avoid that, if I strike with some more angle, something like this, it may be coming like this. Therefore then it goes in the parallel direction. That is the advantage of taking confocal mirrors instead of taking simply the plane mirrors in it. That what we use in the system carbon dioxide laser, we use it. So therefore the three parts in the CO2 laser E are active medium, which is a mixture of gases containing carbon dioxide, nitrogen, helium, and the CO2 molecule will provide the vibrational energy levels. That we'll see it. And pumping is just like a helium neon laser. We use electric discharge only. And resonating column consists of a plane or spherical mirrors which are placed okay, at the two ends of the active medium. That means active medium is in between the two mirrors. This is what we'll have seen for all the three lasers: ruby laser, helium neon laser, and carbon dioxide laser. They have same three components, including, of course, if you add cooling system is also there. Now, what is the construction of the helium neon laser? So we'll take a glass tube or a quartz tube. This is the tube I am taking here, and this is maybe 5 centimeters, 5 meters. Sometimes they say, okay, 5 centimeters long, okay, and then here it is 2 centimeters wide. This is the wide side. And then the diameter of the tube is this. And we apply electric discharge, I electric discharge between the ends of it, and gas gets ionization. And I keep here confocal mirrors to get the resonating column. This is the construction of it. But however, you have to see that the pressures that are maintained in the tube, because I have to give here first carbon dioxide, and I have to keep here the N2 and nitrogen gas, and I have to give here helium, and at different pressures, and I have to evacuate this chamber, and I need evacuation chamber also here. But carbon dioxide is entered into the tube at a pressure of 0.3 tar. Tar is a unit for pressure. 1 tar is approximately 1 mm of Hg, because that is mercury. And helium is at 7 tar, and nitrogen is at 1.2 tar. So by taking the partial pressures of these gases into account, we have kept these pressures, and they will be there. And also the construction is that CO2 is to N2 should be 0.8 to 100. That means 80% of carbon and 100% of, that means for every 100 nitrogen atoms, we have 80 carbon dioxide molecules. So 0.8 is to 1 ratio. 0.8 is to 1 ratio will be carbon dioxide to nitrogen. However, helium should be more than N2. Helium should be larger than this. So that's what we have taken it. And helium plays the same role as that of the helium in helium neon laser. That means it is helpful in achieving population inversion. The output is 10.6. The wavelength emission by the CO2 laser is okay 10.6 micrometers, which is in not in a visible region, but the output is high power output will get in CO2 laser. And if you look at this, the system is figure is like this. Okay, this is a quad tube with a Brewster window, and this is made by NaCl crystal, Brewster angle. Okay, this is the Brewster angle one, and we maintain vacuum inside this, and high power will be given to this to discharge the carbon dioxide molecules and excite the molecules to have undergo vibrational, okay, changes, energy transitions. And we have fully reflecting mirror M2 and partially reflecting mirror to allow the light to come out of it. And we send the gases here. This may be at 7 torr, okay, and this may be 1.2 torr, and this is at 0.3 torr. The pressures. Okay, we'll take the pressure and we send it the gases. The gas will be coming, and here we have the carbon dioxide molecules undergo, okay, vibrational energy transitions, vibrational changes. These vibrational changes will produce the laser light out of it. Therefore, how they are producing this vibrational laser, we have to see it. And that can be understood by drawing a energy level diagram. So this consists of now all this helium, nitrogen, and carbon dioxide. Therefore, carbon dioxide laser is not exactly only containing carbon dioxide. That you have to remember. Okay. And from the partially reflecting mirror end, we will get laser output. This is the constructional diagram of a carbon dioxide, which is almost similar to helium neon laser because the gas is taken in an enclosed tube, discharge tube. Now we look at the vibrational one. See this. This is the carbon dioxide molecule. I told you the carbon dioxide is a linear molecule. Okay, this is the CO2 molecule. We have one C here and oxygen atoms are there at the two ends. So therefore, I write now the oxygen atoms is this. This is also oxygen atom. This is the carbon dioxide atom. This angle is 180 degrees if you take it, and we call it is a linear molecule. And this linear molecule can undergo stretching vibration. See, the atoms, oxygen atoms are stretching, but when they are stretching, they are symmetrically stretching. This distance and this distance are equal, and both of them going away from the central carbon atom. That's why symmetrically with respect to carbon atom, the oxygen atoms are moving, and this is called stretching mode. Okay, symmetrical stretching mode of the carbon dioxide atom. But if you take this, we call it as asymmetric because one atom is going this direction, suppose say the other is going away from the carbon atom. But here, see, both of them going away from the carbon atom, or both of them are coming towards the carbon atom simultaneously. That's why we call it as symmetric stretching. But we call this asymmetric stretching. One is coming towards the carbon atom. This is the carbon atom almost stressed. Other is going away from the carbon atom. Therefore, this distance and this distance, they are not same at a given point of time. And such movement, we call it as the asymmetric stretching. The molecular bonds are stretching. Because of this stretching, there is a energy transition. Okay, this is called asymmetric stretching. So carbon dioxide can undergo a symmetric stretching mode like this, both of them going either away from the carbon dioxide simultaneously or both of them coming, okay, towards the carbon atom simultaneously. We call this stretching mode. But in asymmetric stretching mode, one of the oxygen atom moves away from the carbon atom, other will come towards the carbon atom. Therefore, we don't have a symmetry at any given point. Hence we say it's a asymmetric stretching. Not only this, the oxygen molecules can also bend. See this bending? The central atom is also going up, whereas these are going down. When this is going down, they are going up. This is one bending. Otherwise, they can also go asymmetric bending here also. Okay, one of them. See, they are moving just like this, or they can also stretch like this. This is stretching. Okay, so therefore, the molecules can undergo, carbon dioxide molecules can undergo symmetric stretching, asymmetric stretching, or bending. Okay, like this. The molecules are bending. Okay, see the angle is changing, you see it. They're bending. Okay, here also the angle is changing, the bending is changing. Here this is the angle, but if you see it, this is the angle here. There is a change in the bending or the positions of the oxygen atoms with respect to the carbon atoms. But carbon atom is also moving here. Here if you see it, carbon atom is at rest in symmetric and asymmetric stretching. Only the oxygen atoms are moving. Here all of them are moving, stretching. So as the carbon atom is going up, it is dragging them, both of them up. As it is coming down, they are going up. So these are called the vibrational okay, vibrational energy levels of a carbon molecule, which is a linear molecule. But in the diagram, when you are drawing the stretching, you cannot show by this animation, whatever I am showing here. Therefore, I will show you how to draw this stretching and all that in your notes where you are drawing this. Okay. So therefore, we have here all of them. I will show these three by another static diagram like this. And this is the carbon diagram, central atom, which is a linear molecule. And therefore, if you see stretching mode, both of them are coming close to each other. Okay, they are coming like this and like this. This is symmetric, or they go out and they go out. This is a symmetric stretching mode. Or asymmetric mode is the last one. That means if this is going away, this goes away from it. Okay, if this comes towards this is going away, and if it is coming towards this, it will go away from it. Therefore, we have a symmetric stretching also. That's what we have shown here. If you see that stretching, so this is going here, okay, the atom, but this molecule is coming towards it, is going away from it. Therefore, this distance, whatever you are taking here, this distance is different from this distance. Therefore, we have asymmetric mode of stretching. And vibration means if it is coming down, both of them can go up, or when it is going up, both of them can come down. This is called bending mode. So these figures, this figure, okay, this figure you have to draw when a question is asked on the carbon dioxide laser. Okay, these are the stretching modes. These are the only modes, stretching modes. These modes help us to get the transition, and this can be explained by drawing a diagram called energy level diagram once again. These are the different modes, bending modes, stretching modes, and we have asymmetric stretching modes. These are called, okay, stretching modes. These are called bending modes. So CO2 molecule will have a stretching mode or a bending mode. In stretching mode, we have asymmetric and symmetric stretching modes. And now we look at the energy level diagram, which is a complex energy diagram, which shows the vibrational energy levels of the CO2. So we have nitrogen gas. These are the nitrogen. This is the ground state. Okay, this is the V1 nature. So a higher energy level. We call it as V1 state. And you don't bother about this. This is giving the structure energy levels of different positions. There is no need that you have to remember this. There is no need for this. Okay. Instead of that, these are the different vibration levels they're giving. I call this as a ground level, okay, and we call this as this nitrogen energy levels as something like this. I call it as F1 energy levels ground level, and this is F2 energy level higher energy level. And for corresponding vibration levels for the carbon dioxide CO2 energy level, I call it as E1. Instead of remembering this E001, I can write E2. This is E3. Okay. And this is E4. I can call it as E4. And as usual, when you give the electric discharge, nitrogen atoms get discharged because of the collisions by the helium atoms, what we have explained in the helium neon laser. And the neon atoms are more when compared to nitrogen atoms. Therefore, there is a preferential transfer of energy from the helium atoms to nitrogen atom, and the nitrogen atoms will move to higher energy levels. When they move higher energy levels, their energy levels are metastable states, and they are having okay, CO2 energy levels at the same energy positions. Therefore, the nitrogen atoms will collide with the carbon atoms, because carbon 80 are there, nitrogen atoms are 100 are there, because we have seen that we are taking it 0.80 to 1 ratio, and therefore there is a more chance that the nitrogen atoms will be colliding with the carbon atoms, and thereby you have a collision of nitrogen atoms with the carbon dioxide atoms. Therefore, the ground state carbon dioxide atoms will go to higher state in vibrational energy levels. Once they go to higher energy level, okay, they undergo a transition from E4 to E3, giving rise to the most common wavelength of CO2 laser. Okay, this is CO2 laser energy diagram. Energy diagram I am taking. Energy level diagram you can write. Energy level diagram. So this is what here I am writing. This is energy CO2 laser energy level diagram. You have to draw this also when the question is asked. Then the most important laser, this is the laser light coming out of it, having a wavelength of 10.6 micrometers. But this is this one. Okay, this will give you, this is of course a E3, and of course I'll write this slightly in a different manner. I will write this instead of E4, I make that as E5. Okay, and a little difference is there. This gives you E4. Okay, this level laser, what are both are lasers of course. Okay, but by adjusting the mirror distance, I can change this. So we'll have either 9.6 micrometer laser transition, or you can have a laser transition of 10.6. So both are possible. But by adjusting the distance between the mirrors, if you adjust, okay, these concave mirrors between this one, the lambda can be chosen, and you can have, okay, the required light coming out of it. What I take it, these are the ones I'm taking. So therefore, either this transition or this transition, two are possible with different wavelengths, 9.6 micrometers lambda or 10.6 micrometers lambda. So mostly 10.6 is generally used, but if you want, by adjusting the distance between the mirrors, you can get 9.6 micrometer laser transition also. They are possible. In this way, you can explain the light laser transition in a carbon dioxide one. So what are the special applications of carbon dioxide lasers? So the applications of carbon dioxide laser, if you look at, we have the output of CO2 is very high. Therefore, generally in industries, we use the CO2 laser for cutting and welding. You can cut metal sheets, and therefore the CO2 lasers are generally used in automobile industries to cut, because when you make a car something like this, car will have a body. Okay, and this body where you are taking the car, we have doors also. These are the glasses, we have doors at it, and this should be sharply cut. And to make the body also, they use the CO2 laser to sharply cut the body of this one. And therefore in automobile industries, generally CO2 lasers will be used for cutting, and also they used in some other industries for welding purposes. Okay, this, and we use them for different medical purposes also, to make surgeries, for soft tissue surgeries, used in fabrication of attaching the metal rods by welding. And we also use the CO2 lasers in the treatment of cancer treatment, either non-cancerous or cancerous. Cancerous means malignant cells. Malignant cells, multiply themselves. That's what we call it as unlimited growth. And benign is one non-cancerous. The cells will not be multiplying by this, but you can kill them by using the CO2 laser. You will use it. And in microsurgeries and bloodless surgeries, we use CO2s. But most of the cases, CO2 laser is used in industrial applications. Okay. So I stop here. In the next class, coming class, in the next class we'll see the other parts of this chapter, that is applications of lasers in various fields.